Okay, hello. I hope you can hear me.
Yes, we can.
And you should see my screen right now shared. As far as remember, we just finished with this optical circulator. Yes, am I right? This was the last slide I showed you on the previous lecture. We were speaking about the typical fiber elements. And I showed you the couplers, and then circulator isolator was also. Okay, so let's go to the next element, quite important, so-called optical fiber Bragg gratings. And you somehow just know this phenomena because in the laboratory you had this exercise connected with Bragg diffraction. Here we have something quite similar to this phenomena you met in this Bragg cell, but Bragg diffraction can also act if you are transmitting the light perpendicular to the grating you are making in some media, and the core of a fiber could be such a media. If you just simply modulate the refractive index in the core of a fiber, more or less like this, yeah. So we are introducing small modulation of this refractive index. The distance between this, I mean, the constants of this modulation need to be at certain value, depending on the wavelength we want to operate. We can create so-called Bragg grating, and this Bragg grating just behaves like a mirror working for one single wavelength or some range of the wavelength. So you schematically have has here picture showing you how it is working. For example, if this input signal to such an element is wideband, only one wavelength from this signal is just reflected of this Bragg grating and goes back. And the rest is transmitted. So we can, for example, just cut out some part of the spectra of the bigger spectra, or and simultaneously we are reflecting one certain wavelength or one certain band from the let's say long big bandwidth of continuous waves of different channels or other things. So we are able to just separate different wavelengths of each other using this Bragg grating. Here we have quite typical case of the Bragg grating. I mean, the fiber element you can buy, and of course it is designed for some certain specific wavelength to operate. You will meet characteristics of such a device. Typically, you will see two, let's say, amplitude characteristic, typically the reflection of such a Bragg grating, and also you can meet the transmission. Of course, they are quite supplemental to each other since they are in logarithmic scale, so they don't look exactly the same. I mean, like in mirror, because of the nature of this logarithmic scale. And for the example here, you can see a Bragg grating which is designed to have some flat reflectivity band at some certain range of the wavelength, and of course it is transmitting other wavelength. You can see also second quite important parameter for the Bragg grating, the dispersion. Bragg grating can also introduce some dispersion. So the phase characteristic of such a Bragg grating also is important, and important is to have linear linear phase characteristic for this working operation band for such a broad grating. This one is made for some telecommunication purposes to just simply filter out one of the channels from WDM systems. But Bragg gratings, they can be made in other ways, and they can have quite different characteristics depending what we want to have, for what we want to use such a Bragg grating. For example, special design of the Bragg grating can give us even quite wide reflective band. For example, here you can see a Bragg grating with this band reflected as wide as 37.8 nanometers. Yeah, so we can, for example, just separate not one single channel of other ones, but we can just separate quite big bands from other bands. For example, filtering out third telecommunication window signal from the second telecommunication window signal. Yeah, so we can just separate them quite easily. Also, such characteristics are quite useful for some special applications. This notch inside can be treated as some frequency or the wavelength mark, and using other properties of the Bragg gratings, you can imagine if we have such a Bragg grating, this modulation period depends on the length of the Bragg grating. So if you just simply stretch this structure, of course, this grating is also stretching, so the wavelength reflected by such a grating also is changing. If you are stretching the Bragg grating, you will reflect longer waves than without any stress induced into the grating. The same will happen if you change the temperature of the fiber. Yeah, because of the temperature, also the fiber elongates, so it means we are also changing the period of such a Bragg grating. So in this way we can use Bragg gratings as quite sensitive sensors for the strain measurements or for temperature measurement. And if you imagine on one single fiber, we can just, yeah, we have a fiber. It can be long. It can be just built inside some structure, for example, inside the wing of an airplane. It is quite a popular application of such a Bragg grating sensors. Yeah, so it is built inside the composite structure of this wing in the airplane. We can just make a lot of Bragg gratings in different places. Every Bragg grating can be designed for slightly different wavelengths. More or less like this. Yeah, we are putting some signal, some wideband spectra signal into such a structure, and of course every of these Bragg grating will reflect different wavelengths, lambda 1, lambda 2, and so on to lambda n. So as a reflect band, we will observe different wavelength reflected by each of the grating. Yeah, and changes of this wavelength, changes of the spectra of this signal will allow us to just determine the local temperature or local strain in this certain point where we have this Bragg grating on the fiber. Yeah, so we can use Bragg gratings as a sensors, and we can build using only one single fiber with this Bragg gratings on it. We can use it as a distributed sensor of some different parameters, temperature and strain. This is the most commonly used parameters measured by the Bragg gratings. Yeah, so it is quite useful tool not only for telecommunication but also for some sensing applications. We can make a Bragg grating also in some special design, for example, to modify its dispersion characteristic. I showed you here typical dispersion of let's say filtering Bragg grating. It should be flat or at least linear, but you can imagine we can just make the Bragg grating which has period changing along the Bragg grating, I mean, along of its length. Yeah, so it means from the beginning of this grating, shorter waves will be reflected, and longer waves will be reflected from this, let's say, farther part of this Bragg grating. So properly designing such a structure will allows us to create, in fact, every dispersion profile we want to have. Yeah, so instead of using, for example, dispersion compensating fiber to compensate the dispersion, we can also create some elements which are introducing some certain dispersion for some certain wavelength, and additionally, the shape of this dispersion can be quite easily controlled. For this case, you can see shorter waves will have smaller delay than the longer waves. Yeah, so we can compensate the dispersion of quite long fiber line using such a structure of Bragg grating with not constant period along the Bragg grating, but continuously changing. This grating also will have quite wide reflective spectra. Yeah, so you can imagine it can be also the Bragg grating, which just simply is quite wide band operating Bragg grating. Unfortunately, this structure is band reflecting filter. So to just change the characteristic of such a filter into band pass filter, yeah, this is the thing we want to have mostly. Yeah, to change this reflection into the transmission, we can use the device you already know. I mean the circulator. For example, here we can have a couple different channels transmitted through our erbium doped fiber amplifier, and we want to just simply choose one of them and transmit to the photodetector, and the rest should be just transmitted in other path of our system. So if we just simply put such a signal through the circulator to the Bragg grating, only one of these channels will be reflected and go to the photodetector, and other channels, they will simply go through the Bragg grating and go to other parts of our system. Yeah? So using the circulator and Bragg grating together allows us to change this reflectivity characteristic into the transmission characteristic. So from the third port of the circulator, we will see the transmittance characteristic looking more or less like that. Yeah, so this reflective characteristic of the Bragg grating will turn into transmission characteristic if we just observe the signal on the third port. There are also different possibilities in the Bragg grating. Sometimes we want to only just cut some band of the signals, but we don't want to reflect. Then we can met the Bragg grating, which isn't written on the fiber exactly perpendicular to the fiber axis, but if you just simply make the Bragg grating on the fiber at some angle, for example, in this way, you can imagine this certain wavelength which is reflected will be reflected off the fiber, so it will not be transferred to our source. It won't create some back reflection, but it will be just simply attenuated. And then Bragg grating will act like a band block filter without any reflection. For some certain very specific applications, it is also a necessary device. So then you can use this specially designed Bragg grating, which doesn't have any reflection, but it has only attenuation because of this reflection going out of the core of a fiber. Yeah, the angle is chosen to be bigger than this critical angle inside of the fiber, so all the reflected beam will just leak out of the core of the fiber, and it will not be guided in the core. Yeah. Another devices which are sensitive to the wavelength and they are quite useful. In fact, you are meeting with these devices on the laboratory. This exercise with this erbium doped fiber amplifier, just to connect two signals together. I mean the signal to be amplified at the wavelength 1550 nanometer and pumping signal for our erbium doped fiber amplifier 980 nanometers. So we are using specially designed coupler, so-called WDM coupler, wave division multiplexing coupler, and they have slightly different construction. They aren't basing on the Bragg grating, they are basing typically on some filtering layers inside of such a structure. They can be made differently using some, this should be lens, not the Sochevka. Lens green lens. In fact, this is green is taken from gradient index, so it works more or less like gradient index fiber. Yeah, so cylindrical structure which is bending the rays propagating inside of it allows to quite easily couple the optical fibers to such a structure. And if you just simply put some filtering elements, some mirror, which is operating at different wavelength, I mean, one wavelength is reflected from such a mirror and other wavelengths are transmitted. So it allows quite easily to create this WDM couplers. Yeah, this is very typical approach how to make this WDM coupler. And they are quite useful devices just to joining or splitting two different bands of the wavelengths, because typically it works, it has the characteristic not as narrow as Bragg gratings, but they are working more or less like band, I mean low or high pass filters. Yeah, so for example, this reflection can work like this. Yeah, this will be the reflection of such a layer for lower wavelength. I mean, for shorter wavelength, they will be reflected, and longer wavelength will be transmitted through such a filtering element. So we will have something with just splitting two different bands of the wavelengths from each other, or opposite, if we just simply put the signals in opposite directions, they will be just joined together into one common fiber. It acts more or less like this. And I think regarding this, let's say, passive components, at least for now, it can be enough. The next quite big group of the optical fiber elements, they are active components of fiber systems. We can have two main groups. The first one is mostly connected with, let's say, sources and detectors, and other big group and all the time developing, they are optical amplifiers. So they are appearing mostly in telecommunication, but also using these optical fiber amplifiers, we can build, for example, lasers, fiber lasers. To some certain applications, fiber lasers has quite high advantages over classical lasers. So you can use active fiber as a gain media to create a laser. On the lab also you are measuring such a laser. This Q-switch, I mean this pulsed fiber laser, is made of erbium doped fiber amplifier. So some quite important part of this laser that there is a erbium doped fiber amplifier inside of the resonator of this laser. Okay, so starting from the light sources, of course, you know already for fiber technology, in practice only semiconductor lasers are used. Sometimes also you can make light emitting diodes coupled with the fibers, but these LEDs are mostly coupled with multimode fibers because of the nature, you know, multimode fiber has much bigger core diameter. So using not coherent source is relatively easy to pigtail with such a multi-mode fiber. For single mode fibers, practically you can only meet as a light source the semiconductor lasers. Yeah, because of the nature, because of the properties of such a structures. Of course, you know already, I think, everything you need to know regarding this semiconductor laser. So I don't need to explain you how they are operating and other things, but having the light source is the one point. The second point is how to modulate how to put the information into this, let's say, our optical signal. So something connected with the light modulation is important to just show you. And the most simple approach could be direct modulation of the lasers. Yeah, semiconductor laser, you know already the characteristic of such a laser regarding the current. You remember, if we are controlling the semiconductor laser, we are controlling the light, the current driving the laser. And of course, we are changing the power of such a laser. Yeah, so you remember the characteristic, you measured them on the laboratory. This area of operation, this is LED, so the light isn't coherent. The modulation coefficients aren't high because, you know, the intensity is quite low, you can see. And also the speed of such a modulation is extremely low. If you want to modulate the laser efficiently, I mean with high frequency, we need to modulate the laser on this part of its characteristics. So we need to operate above this threshold current. Yeah, so just to simply modulate the power of the laser, we are modulating the current of the laser, but all need to be done above the threshold laser. If we start to modulate below threshold laser, threshold current and above, we will have quite big penalty for a delay connected with this turning on the laser radiation and then switching off the laser radiation. Yeah, so we'll have much slower modulation in such a case. To have to modulate laser fast enough for high speed modulation purposes, we need to modulate the laser in the area of the laser action above the threshold current. It is quite easy to modulate the laser in such a way. So this is the main advantage. Yeah? It is simple to modulate the laser directly. You can modulate almost every semiconductor source in this way. So the applications are quite wide, but of course the disadvantages of such a modulation, some of them I already mentioned. They are very sensitive to the operating point. It means it requires to precision control the temperature. You remember, if we are just simply changing the temperature of the laser, the characteristic is moving to the right or left, so also the threshold current is moving. And I told you already, we need to keep all the modulation above the threshold current, but as close to the threshold current as possible, because we want to have high modulation contrast. Yeah, we want to have zero to be almost zero light. As small light as possible should be our logical zero transmitted by such a structure. Yeah, so operation well above the threshold current will give us zero, not to be exactly the zero, and it will be much more difficult to detect later on, to distinguish between zeros and one. So it is important regarding the transmission of the data to have so-called extinction ratio as high as possible. Extinction ratio is something close to the contrast of our output signal. Yeah, if we are modulating the intensity of the light, yeah, and the time. So in time domain, our modulated signal will look more or less like this. And we want to have this zero as close to the zero as possible. Of course, we cannot have exactly zero because, like I told you, we cannot be below the threshold current. Yeah? So even if we are transmitting logical zero, we will transmit some very small amount of the light through the fiber. So changing this zero And modulating in such a way, of course, will give quite hard to then distinguish between 0 and 1, especially if you just simply add additional noise to the signal and other things which are appearing after some distance of the transmission, maybe some amplification also and other things. So this extinction ratio for the modulation is extremely important parameter to have as high as possible this parameter to be able, because it also increases the immunity to the noises and other things. Other problems connected with this direct modulation of the laser, you can match such a behavior of a laser. If you are turning on the laser, you can have at the beginning of the pulse, of the light pulse, some relaxation oscillations. They can appear. Yeah, it don't happen always, but for some lasers design, it may happen. And of course, we don't want to transmit the pulses in such a way, because you will have additional information and additional modulation to our signal. If you want to just transmit square wave, we want to have also light of this shape, not the light which has additional oscillations on it. Another thing which can happen, laser after turning on can slightly change the wavelength. Yeah? So we can also induce some laser tuning which will appear as so-called chirp of the laser pulse. For example, turning on the laser, the intensity will be as follows, but the wavelength will change continuously in such a pulse, for example, from lambda 1 up to lambda 2. Yeah, typically from the shorter waves to the longer waves. So you can imagine such a behavior will, for example, make the spectra of our transmitted signal not so narrow like we want to have, but it will be broadened, in fact. And you remember the issues connected with this chromatic dispersion. We want to have as small bandwidth of our transmitted signal as possible regarding these dispersion effects. What else? Maximum frequency of such a modulation is up to couple gigahertz, and we cannot go further. This is the, let's say, hard limit, which is built inside the semiconductor and connected with carrier lifetime in such a semiconductor. These hard limits you can see, for example, right now in the development of the microprocessor. I mean, these CPUs we have in our PCs, they just hit this 5 gigahertz barrier, and the further increasing the frequency of operation for our microprocessors is extremely hard. And in fact, for silicon, for example, this 5 gigahertz and very small fraction above it is not to be easily overcome. Changing the semiconductor, for example, to gallium arsenide would help, but gallium arsenide for, let's say, typical electronics, it would be extremely expensive solution. So this is why they are basing on silicon, and we have some limits at the maximum frequency of the microprocessors right now. The development of this increasing of the frequency has stopped, in fact, right now. They are increasing the frequency from generation to another generation by 100 megahertz or even less. And that's all, yeah, because the same, of course, applies to the modulation of the semiconductor lasers. So couple gigahertz, this is the maximum we can have for such a modulation. And it cannot be improved in any way using the direct modulation of such lasers. So for higher bandwidth applications, we are using external modulators. And the first one, you can be familiar with it on the laboratory, because you are measuring the characteristics of such a modulator, Mach-Zehnder modulator. I think this device looks familiar for you if you made already this exercise with this Mach-Zehnder modulator. It is quite simple device using electro-optical effect to just change the refractive index of a planar fiber. The whole modulator is made of the planar fiber in the lithium niobate crystal typically. So we have the interferometer. Yeah, so we are putting the light from the input. It is divided into two independent beams, and then they are meeting together in this output fiber. So in this coupler, we have some interference between these two beams, and depending on the phase difference between them, we will have maximum light intensity or minimum light intensity, depending on the phase difference. And we can control the phase of these two beams just simply applying a voltage to this fiber at this certain distance. So we have some electrodes which are just deposited on this structure, and we are able to control a phase of every of these two beams. So we are modulating the phases. And after interference, we have the amplitude modulation. Yeah, so typically, of course, two electrical inputs bias to just set the operating point, and RF input. For this modulator, you can see special connector. This is SMA. If I look, if I can see it clearly here. SMA connector for higher frequency signals, of course. SMA, it is working up to 10 to 5 gigahertz quite nicely. For the higher frequencies, other types of connectors are used, but as you can see, this type of modulator is able to operate even at 40 gigahertz bandwidth. So we can use such a modulator to the modern telecommunication systems, because this 40 gigabits per second, this is, let's say, typical modern telecommunication system. They are using such a fast modulation, and they are typically fiber pigtailed. Input fiber, typically this is PM fiber, because the whole device is quite sensitive to the polarization. So we need to just maintain and to control the input polarization for such a modulator. So typically it can be or connected with the laser directly. So we can just put a chip of laser and close it to this structure and transmit the light from the laser directly to this planar fiber, or we can couple this planar fiber with this external fiber, but this input fiber typically is PM fiber because we need to control the polarization of the input signal. Yeah? And then it allows us to have constant in time characteristic of such a modulator. What else? So these are advantages. Disadvantage, of course, they have a couple of them. High insertion losses, especially regarding this fiber coupling, because planar fiber typically has different mold shape. For example, it isn't Gaussian because of the geometry of this planar fiber. Yeah, you remember it is some rectangular structure. So you can imagine the mode field in such a structure is somehow elliptical, and you cannot couple such a mode into the, let's say, cylindrical fiber without significant losses. So a couple of dB losses we have on such a structure. It isn't so important regarding that typically we are putting such a modulators directly after the laser. So we can just simply increase the power of the laser just to compensate it. And the second disadvantage, they are sensitive to the polarization. So they are required to use PM fibers on the input side. Yeah, so, but this solution, I mean this Mach-Zehnder modulator, this is the most commonly used modulator for modern telecommunication systems, especially for these, let's say, standard ones. But if you want to go to some extreme modulation frequencies, extreme modulation speeds, there are also limits connected with these planar fibers and the maximum frequencies we are able to have in such a modulator. You can imagine we have some capacitance here on these electrodes and other things which are preventing us to go with this frequency higher and higher. So then another phenomena in the semiconductors can be used, and it is some kind of quantum effect, Franz Keldysh effect, and it appears in so-called electro-absorption modulators. Electro-absorption modulator is basing on the phenomena we are changing the band gap in the semiconductor, applying external electrical field to this semiconductor. Band gap in the semiconductor, you know what the band gaps in semiconductors is, but this band gap also defines so-called absorption edge for the semiconductor. If you look at the absorption coefficient or the spectral properties of the semiconductors, I mean, what wavelengths are absorbed by the semiconductor. Yeah, so here we will have absorption and the wavelength. So semiconductors typically are absorbing the short waves, and at some certain wavelength we have extremely step characteristic of starting to be transparent. Yeah, for example, for silicon, this wavelength is typically at 1.1 micrometer. For different semiconductors, it can be different value. Of course, the smaller band gap will be this absorption edge. Of course, will move to the right. So for the semiconductor from A3B5 group, yeah, you know them. For example, gallium arsenide or indium gallium arsenide and other compositions of such a semiconductors. This edge can be at much higher frequencies, much higher wavelength, not the frequencies, lower frequencies. In fact, yeah, they are inversely proportional to each other. So above this wavelength, they start to be transparent. Yeah? This is why, for example, the silicon detector cannot be used for second and third telecommunication window, because the silicon is transparent for this wavelength, so it cannot be absorbed. It cannot create this electron hole pair just to create the current driving to our photodetector. And this edge is slightly dependent on electrical field inside of such a semiconductor. So applying external electrical field, we can just simply slightly move this absorption edge. So if we have a laser operating near this absorption edge, changing slightly this band gap energy can act like some kind of a shutter. Yeah, if we just simply move this absorption edge, this is the transmission versus so transmission. Yeah, so the left side is absorbed, so increasing the voltage will just move our absorption edge to the left, so it slightly increases the band gap of the semiconductor and makes this semiconductor start to be transparent for this certain wavelength. You can imagine this movement isn't so big, so for this photodetector will work only for one certain specific wavelength it is designed to operate. But if you remember how we can control the wavelength of the semiconductor laser, we are controlling it directly using the same effect. I mean, this band gap relation to the wavelength emitted with the wavelength emitted by the laser. So in fact, exactly the same type of the semiconductor can be used for making the light source, and next to this light source we can just build such a electro absorption modulator. The huge advantage is this phenomena is extremely fast. we can have up to 100 gigabits per second, or even higher right now, because I made this slide a couple years ago. Right now, the record values are much bigger. They can be integrated with this laser, and typically they are integrated. Of course, some limits, they are expensive, because the price of such a modulator will be quite similar to the price of a laser. The technology will be exactly the same, and additionally, regarding these extreme high operation frequencies, they will require quite specific approach regarding these high frequency signals. And the last limit, which can be quite important for some applications, they are inducing chirp to the signal. You can imagine, during the modulation, we are constantly moving this absorption edge. So if our laser has some certain spectra, we are opening the spectra from the right to left and changing the spectral properties during our opening and during closing of this modulator. Yeah, so we can, in fact, the chirp is built in the principles of operation for such a modulator. But huge advantage, they can be just simply integrated with the light source, made in one and the same technological process. And here you have some example of such a module. We have a laser. Here is the laser section, DFB laser in this case. And here we have the modulator section. Of course, these electrodes to the modulator and all other things which is designed to operate with these microwave frequencies, because this one is not for such a high frequency, because it is 10 gigabits per second module. But as I told you, the frequencies for such a modulators, they can be even 100 gigabits per second, so they can be extremely high. The highest, in fact, possible regarding this these external modulators which are used for the telecommunication applications. Okay, so yeah, this is the last slide for this presentation. I should show you on the previous lecture. So right now we can go to the next group, quite big group of the active devices in the fiber systems. I mean photodetectors, but not only photodetectors alone, but the whole receivers, because in fiber systems we can match not single photodiode, but complete receiver, including inside some amplification circuits and even some logical circuits to clock recovery and to create from analog signal, create some digital signal to the output compatible with this next part of our telecommunication system. So these are optical receivers, and they are consist of couple parts. Typically for the detectors, we are using now semiconductor detectors. Here you have typical spectral response of different semiconductors. This absorption edge I showed you on this with this electro absorption modulator. So you can see also here, semiconductor became transparent for these longer waves, and the type of the semiconductor determines the wavelength range which is possible to detect using such a semiconductor. Here you have typical parameters of such detectors, peak response, responsivity, quite important parameter, and these are the limits. For silicon, for example, the maximum responsivity of such detectors is half of amperes per watt. For gallium arsenide, it is 1.1 ampere per watts of radiation, which is incidenting on the photodetector. And the rule is the spectral responsivity is quite highly dependent on the wavelength. You can see for silicon, the same also for indium gallium arsenide photodetector. We have the sensitivity depending on the wavelength and increasing with the wavelength. And it could be quite a nice question for you right now. Could you just explain why we have such a relation? Why the sensitivity of the photodetector is dropping with the decreasing of the wavelength of the signal? Do you have idea why it is in this way? This question is just to wake you up.
Our signal to noise ratio?
Not. It is more from some quantum nature of the photodetectors and some, let's say, properties of the light also. Do you remember the parameter of semiconductor lasers, which you should just calculate, at least at home after the laboratory? I mean, this quantum efficiency of the semiconductor laser. Yeah, for source, you can just define this quantum efficiency. For the photodetector, you can also define a quantum efficiency. It is the amount of the electrons of the photocurrent created by some certain amount of the photons. But you can see it is even for this quantum efficiency equal to 1. Yeah, so for ideal photodetector, we cannot have more electrons flowing through our photodetector than amount of the photons. So the photons, the amount of the photons, how could you calculate? Knowing the optical power, for example, yeah? Are you able to calculate, for example, for 1 watt of optical power, are you able to calculate how many photons per second is in such a light beam? How we could calculate the amount of the photons, knowing the optical power? We should go from the definition of the power. Power is some energy over the time, yeah? So, if we know the energy of 1 photon, every photon has some energy connected with it. Do you remember the equation telling the energy of the photon? Quite simple formula. It's telling us what is the energy of the photon. Planck constant and frequency of the light, of this photon, yeah? The frequency can be calculated, of course, as a c over lambda. C, speed of the light, lambda is the wavelength. So the energy of 1 single photon, you can see it is equal to, so the shorter the wavelength is, the higher energy of the photon is. Yeah. So if we have, for example, 1 watt of optical power, it means if we have short wavelength, we will have small photon amount per second. And in infrared radiation, for the same optical power, we'll have much more photons. So for longer waves, we will create more electrons as a photocurrent. Yeah. So decreasing the wavelength is increasing the energy of 1 single photon. So for constant power, we will also decrease the amount of the photons. Yeah, quite easy to understand. But at first, it can be quite weird why it behaves in that way. And this is the reason why. It is strictly connected with the energy of 1 single photon. Yeah, so this is why, for example, detecting of the ultraviolet radiation is quite difficult because of this nature of the light. Yeah, to detect small optical powers at this range, we are dealing with the small amount of the photons, also much smaller than for infrared radiation. Okay, so let's go to some basics of photo detections. I think you know it already, but just to remind you some basic effects we are dealing with. So photodetector typically, and the first approach to photodetector is PN photodiode. I think you can also name another semiconductor photodetectors. Do you know other types of photodetectors made of some semiconductors? Do you know other types of photodetectors?
CCD?
CCD, yeah, but it is basing, I mean, single point photodetector, because CCD, in fact, is the matrix of photodetectors. And for CCD, we have some, you can name it phototransistor, photomOS. Yeah, in CCD, we have MOS transistors with the gate, which is charged or discharged by the photon energies. But regarding, let's say, classical photodetectors, I mean single point. Yeah.
Film, maybe?
Once again, please.
Film.
Film. You mean some photosensitive chemical material, yeah?
Yes.
Yeah, but of course, the speed of the detection will be extremely low. Couple days even, yeah? So the period of our detection. I thought mainly about some semiconductor detectors. Historically, for example, some photoresistors, they were the first photodetectors which were available. So we had just one single type of the of the semiconductor with 2 electrodes, and applying light to such a photodetector. Yeah, so we have 2 electrodes. Applying the light, of course, induce these electron holes pairs, allows us to change the resistance of this structure. Yeah. But they are extremely slow. The frequency of the operation for such a photodetector is extremely slow because of the nature. The same nature prevents us of using PN photodiodes in, let's say, high-speed applications. So PN photodiode is, in fact, some historical point of developing the photodetectors. Yeah, it works in quite simple way. We have P layer, N layer, and this depletion region here. Yeah, depletion with quite high electrical field. We just simply separate the carriers of each other. So if we just create electron hole pair somewhere in depletion region, they are quite fastly separated by this electrical field, and they are creating photocurrent. But what will happen if the photon will be absorbed in this region or this region? Yeah, so we are creating the electron hole pair here or here, because we have no guarantee that the photon will be absorbed only in depletion region. It can be absorbed on the whole depth of this structure. So every electron hole pair created here, these carriers are moving extremely slowly because the mechanism of the carrier movement in these layers is the diffusion, and diffusion is regarding the time scale, of course, is extremely slow process. Typically, it is couple nanoseconds per 1 micrometer of the distance to travel. Yeah, so you can imagine couple nanosecond of the delay introduced to such PN photodiode, because we cannot guarantee we will have no carrier creations in these two regions. This drift separation and drift limits, they are much faster. So the limit for standard PN photodiode, this is this drift of the carriers in these P and N type layers. So PN photodiodes are slow. The maximum frequencies are ending something close to, let's say, 10 megahertz, and that's all. Yeah, so we cannot use them for high frequency, high bitrate communication systems because of this thing. But how we can improve it? How we can improve it? Additional limit here is also the capacitance of this junction, which is given by the area of this P and N type layers, and of course distance of depletion region. It works more or less like capacitor. Yeah, so the capacitance of such a device will be also quite big, because this depletion region typically is pretty thin. So capacitance also will be quite big, and it also limits the maximum frequencies in such a device. So just to solve this problem, another type of the photodetector was invented, and in fact, these PIN photodiodes, they are widely used in the telecommunication, and not only the telecommunication, because they are, let's say, they made some compromise between the sensitivity of such a device and the speed of their operation. I mean, the maximum bandwidth for such a device. We are adding some intrinsic semiconductor between these P and N layers, which allows us to extend the length of this depletion region. It is the first thing. Yeah, so we are decreasing the capacitance of such a junction at first, but additionally, we can make this structure as so-called hetero structure, and you can see here typical construction of PIN photodiode. This intrinsic layer, which is operating as absorbing layer, has different semiconductor than these external layers. This P and N layer, they have, for example, here indium phosphoride. Indium phosphoride has higher band gap energy than indium gallium arsenide. It means for some certain wavelength bandwidth, they are just transparent. So we are avoiding, in such a way, we are avoiding to creating the electron hole pairs in these layers. Only in intrinsic layer, the electron hole pair can be created. It means only this this mechanism connected with the electrical field forcing to move the carriers is useful in this device. So only this one is limiting the maximum maximum frequency of the operation for such a photodetectors. So they are much faster. Additionally, this intrinsic layer can be quite thick, so the absorption can be quite big in this layer. We can just design such a photodetector to have almost 100% of the absorption in this intrinsic layer. So the sensitivity of such a photodetector can be good. For this indium phosphoride semiconductor, the band gap, so the absorption edge is somewhere close to 1 micron, and for indium gallium arsenide is at 1.7 micron. Yeah. So if you just put the photons from this range, I mean between 1 micron and 1.7 micron, they will be absorbed only in this layer, in this intrinsic semiconductor. So it allows to significantly increase the sensitivity from one side and the bandwidth of such a photodetector. Here you have typical data for different types of the semiconductors. As you can see, for the telecommunication applications, also germanium photodetectors can be useful, but they aren't used because of this important parameter. You can see typical parameters of such a photodetectors, and dark current is a quite important parameter regarding something similar to this extinction ratio for the transmitters. I told you here we have dark current. Even without any photons going to the structure of the photodetector, we will have some current flowing through the junction and masking as low intensity light. Yeah, if the power of the input signal is small, it can be just masked by this dark current. And as you can see, for germanium, this dark current is at least one order or more, or even 2 orders of magnitude higher than for silicon or typical indium gallium arsenide photodetectors, which are for telecommunication. The bandwidth, I told you previously, the same for the direct modulation of semiconductor lasers. Of course, it is also true for the detectors. The fastest detectors can be made of these A3B5 group semiconductors. The silicon is much slower. As you can see, germanium can be slightly faster, but germanium isn't useful because of this dark current. And bias voltage, because I think you know the photodetectors, photodiode structures, they require to be polarized in this negative, in this opposite direction, not to be conductive, but in this second opposite voltage need to be applied to this junction. So bias voltage also is different for different types of the photodetectors. And you can see the indium gallium arsenide. I forgot to tell you. You can see it is operating. It is given the operation from 1.0 micron, but the characteristic starts from even 800 nanometers, because this is the characteristic for such a modulate, such a photodetector. But you can see quite significant drop in this responsivity. Yeah, we can just draw 2 lines. One for this wavelength range, and second for this one. For this one, we will have operation and absorption of the photons only in this intrinsic layer. But here, the photons will be absorbed also in this N and P type layer. It also means the photodetector for this range of these wavelengths operating, it will be much slower than the bandwidth they are guaranteed in the datasheet. So this is why they are giving the wavelength bandwidth from 1 to 1.7 micrometer, not from 800 to 1.7 micrometer, because for this range it will be slow, exactly the same like for standard PN photodiode, and the same reasons. We'll have additionally drift in these P and N layers of semiconductor. Okay, but you can imagine 10 gigahertz, it isn't the bandwidth enough for the, let's say, some extreme or modern telecommunication systems. So there are a couple different approaches to produce and to create the photodetectors, which has even higher bandwidth. They are all basing on this pin structure, but the approach is changing because to increase the frequency of the operation, we need to change the geometrical parameters of this intrinsic layer, decreasing the area of the junction, in fact, to decrease the capacitance of such a junction. So we can have, for example, resonance. So they are sacrificing the sensitivity to the higher frequency, and of course, if we are sacrificing the sensitivity, we need to find a way how to improve this sensitivity in other way than geometrical. So we can have different possibilities. The left one is resonance cavity enhanced. So it means we have two mirrors forming some kind of Fabry-Perot resonator between them. Additionally, these mirrors, they can be made as a Bragg reflector, so they can just operate at one single wavelength. So it allows to create the fast photodetector and additionally quite sensitive to the wavelength. So this photodetector can be designed to detect only one single channel from WDM systems, for example. Another approach can be using sight, introducing the light into the structure, just to increase, of course, the absorption length. So we can just introduce the light from the side. So in similar way, like we have emission from the semiconductor laser, the same we can apply and introduce the light from the side to such a structure. So we don't need to have also the big absorbing layer regarding this direction, and we can also have quite high absorption coefficients and increased the bandwidth of operation for such a photodetector. And for extremely high frequencies photodetectors, we need to also consider all the wave phenomena which can appear and which are appearing if we are dealing with extremely high frequency signals. You can imagine 40 gigahertz signal. This is the microwave signal. So the electrodes of such a photodetector need to be also need to have some certain dimensions, creating a waveguide for electrical waves. So we have a waveguide for light beam in this intrinsic semiconductor, but also we are creating some waveguide structure also for electrical signal, just to have this impedance matching between our photodetector and the other parts of our circuit and other things. For microwaves, the rules of we cannot just simply put a wire for the microwave signals. So this is why these traveling wave photodetectors are appearing. So they are designed as a microwave structure, waveguide structure for this microwave signals detected by such a photodetectors. And these microwave detectors, of course, they are designed for certain bandwidth. They aren't able typically to operate from, let's say, 0 hertz up to the maximum value, but they are designed, for example, for from 10 gigahertz up to 20 megahertz of operation or something like that. So we have one approach of which can sometimes is used, just we want to increase the frequency of operation, but sometimes also the important parameter, the most important, is the sensitivity of the photodetector. And here we can use so-called avalanche photodiodes. Avalanche photodiode is the photodiode where we have amplification inside the structure of the photodetector at once. Yeah, so the structure is in fact the same like pin photodiode, but we are applying so high voltage to such a structure in this reverse voltage. Yeah, so if we just simply draw this band model of our photodiode, P and E, of course, like previously, it is heterostructure, so absorption can be done only in this intrinsic layer. Yeah, so we are creating electron hole pair. They are, of course, separated by this electrical field, but the electrical field is so high, it is close to breakdown voltage for such a structure, that the velocity, the energy of this electron, of course, is increasing. Yeah? It is accelerated by this electrical field, these electrons here, and this energy can be higher than ionization energy for this semiconductor. It means the electron can hit one of the atoms of this semiconductor and it can create another electron hole pair. Yeah, so we will have creation of additional electricity carrier here inside of such a structure. So one photon falling on such a structure can create, for example, 2 electrons of the photocurrent. So the quantum efficiency for such a device will be higher than 1. Yeah? I told you previously the quantum efficiency, the maximum value is 1. It is true for standard devices, but if we will have this avalanche multiplication, of course, the quantum efficiency will be higher than 1, because 1 photon will create at first 1 pair of the electron hole, but the pair of electron hole can create additional these secondary pairs because of this high energy acceleration in this intrinsic layer. Yeah, so structure of such a and we can change this multiplication factor, changing this reverse voltage applied to this photodetector. The structure is pretty similar to PIN photodiode. So this first approach, in fact, it is exactly PIN photodiode. The only difference is operation very close to this breakdown voltage, but of course it has quite big disadvantages. I mean, this classical approach, every, let's say, spontaneously created electron hole pair, which creates this dark current in typical photodetectors, in this approach, they are also creating this photocurrent. I mean, they are also creating this multiplication by this APD photodetector. So for such a structure, this dark current will be also magnified, and unfortunately, they will be multiplied more than multiplication of the photon signal. Yeah, so dark current will mask even more our weak optical signals for such a structure. So the solution for this thing is to just simply separate the absorption and multiplication layers or areas in our semiconductor structure. The band model for this sum APD looks more or less like this. Here we have low gradient of the voltage, and here we will have this high gradient. This one is made of the semiconductor indium gallium arsenide. So absorption will be only in this layer where this slope, this electrical field isn't so big. If it isn't so big, it means we have no this avalanche multiplications. We only just creating the carriers. The multiplication is taken in this layer of the semiconductor, I mean in this multiplication layer, which is made of indium phosphoride, which has greater band gap energy. It also means the greater band gap energy means the creation of these dark current carriers is much less efficient, because creation of these dark current components is mainly because of the thermal effect. The smaller the band gap is, the higher dark current will be. So if this material, it can be quite thick, but if the band gap for this material is much bigger, this, let's say, influence for the dark current of this part of the photodetector will be much smaller. So the only source of the dark current will be this absorption layer, and it can be quite thin, in fact. Yeah. So if it is thin, so the low volume of dark current creation, we will create only these electron hole carriers in this layer, and multiplication will be taken in this second layer. But it, of course, it just improves these dark current issues, so the sensitivity can be much higher for such a photodetector, but decreases, unfortunately, the bandwidth. So the last evolution of the APD photodiodes is additional layer between the multiplication and absorption layer, so-called grading layer, because adding a step to this band pass model, I drew you previously. Yeah, we have different band gap for absorption and multiplication layer. This step in this band gap energy is introducing some phenomena which are making such a photodetector to be much slower. To avoid this problem, they are adding additional layer, which is a way how to more smoothly transfer from, let's say, high band gap energy layer into low band gap energy layer without slowing the carriers on and so on. Yeah, it is much more complicated to just explain you because a lot of quantum effects are playing role here to this grading and to explain how it works. So I think it is enough for you just to know the grading layer is just to increase the frequency of such a photodetector. I mean the bandwidth of such a photodetector. Yeah, so we have some solution how to have extremely sensitive photodetectors. So the last type of the photodetectors, which is used where typical pin structure isn't enough regarding the speed of the operation for such a structure. These are semiconductor metal photodetectors. You know, this junction between metal and semiconductor is so-called Schottky junction. Yeah, so I think you know also Schottky diodes. Yeah, do you met with this name, Schottky diodes, or not? You didn't hear about the Schottky. Schottky diodes are very fast. They are used for example, rectification of high frequency signals for, let's say, also for some detection. This metal semiconductor junction is extremely fast because of this of its properties. The same, of course, applies to the photodetector. We can create the photodetector using this junction, and because of the properties of this junction, this type of photodetectors, they can be extremely fast. As you can see, even hundreds of gigahertz, this can be the bandwidth of such a photodetector. So in fact, way above the microwave frequency area. So we are going to terahertz waves, in fact, hundreds of gigahertz. They can be produced with quite low cost because they are simple structures on the semiconductors. But of course, there are some prices we need to pay for it. The main price is low sensitivity of such a photodetector, yeah, and also high noise. It is connected with this low band gap energy for the Schottky barrier. It is the reason why they are so fast, but from the other side, other hand, they had quite high dark current, for example, and other things. And typical parameters for such a photodetector. This is some commercial one, so you can see the bandwidth somewhere between 20 and 35 gigahertz. The wavelength range of operation can be quite wide, but the responsivity, as I told you, pretty small. Yeah, something around 0.2 amperes per watt, so almost 5 times smaller, excuse me, than for typical pin photodiode. Yeah. This is the main disadvantage of such a photodetectors. This low sensitivity is given by this not so thick junction, but also since we need to have junction between metal and semiconductor, the metal layer here need to be transparent. Of course, it is very thin metal layer, but it absorbs, even though it is thin. So this metal layer is absorbing quite big amount of the photons which are falling on this photodetector. So this is the second reason, especially the reason I told you previously that the sensitivity, the responsivity should increase with the wavelength, but looking at this data, you can see it is almost constant, doesn't matter the wavelength, because the absorption in this metal layer is also proportional more or less to the wavelength. Yeah? So increase in the responsivity with this wavelength is also goes in par with this increase in the absorption in this metal layer. Excuse me. And just to summarize our photodetectors, as you can see, some historical photodetector just to see how they are operating. PN photodiodes, the main and the most important photodetectors, PIN photodiodes. If we want to have extremely sensitive photodetector, we can have this avalanche photodiode. If we want to have extremely high bandwidth photodetectors, we are using MSM photodetectors, and this responsivity improved in this APD by this factor of multiplication, avalanche multiplication. It can take the values from 1 up to the hundreds or even thousands, but the rule is to have high multiplication, we need to be very close to this breakdown voltage for such a photodetector. So they are requiring quite sophisticated power supply units to keep the condition of operation for such detector in, let's say, safe areas. They are also sensitive. This multiplication is sensitive to the temperature and other factors. So the power supply for such a photodetector, it isn't easy task to make it. And in fact, typically the photodetectors, these APD photodetectors, they are somehow integrated with this power supply already in one, maybe not a chip, but one, let's say, some hybrid structure. So because the power supply voltage for such a structure need to be at least couple tens of volts, yeah, because it need to be close to this breakdown voltage. I think for today we can just finish because we are right on the time of ending of our lecture for today, and it doesn't make a sense just to start next quite big group of the optical elements, because next part will be about optical amplification. Yeah, so optical amplifiers, there are a lot of types of optical amplifiers. One of them you are meeting on the laboratory, Erbium fiber amplifier. Yeah, so if you have questions connected with today's lecture, of course, it is good time for making them, for asking them. If not, thanks for your attention. And of course, we'll see on the next lab on Monday. Okay, so you don't have questions, so bye-bye and see you next time.